Hello dear students, welcome to the course of Engineering Thermodynamics. Myself Mihir Mistry, Assistant Professor from Mechanical Department of LJ Institute of Engineering and Technology. So today we are going to continue our session on refrigeration cycle, and in particular we are going to discuss some example on refrigeration cycle. So let us start with the given data. So as you can see on the screen, a food storage requires a refrigeration capacity of 12 TR. Now here students, TR, that is nothing but ton of refrigeration. That is a unit used in refrigerations, that is ton of refrigerator. So ton of refrigerator means what? Very simple, let us understand that. It is the amount of heat removed from the atmosphere in order to melt 1 ton of ice during one day. Okay, I am repeating again, amount of heat removed from the atmosphere to melt 1 ton of ice during the time period of one day. That is equivalent to 1 ton of refrigeration. Okay, so as you can see, I have written 1 ton of refrigeration TR, that is the abbreviation. So 1 TR is approximately equal to 211 kilojoule per minute or 3.5 kilowatt. Okay, so here 12 TR is given, that will be equivalent to 42 kilowatt, right? So ultimately this TR, ton of refrigeration, means what? That is our target, that this much heat shall be removed. So here the target is 42 kilowatt of heat shall be removed continuously. So that is ultimately our refrigerating effect that is given to us. Okay, clear? Now let us read the data further. So works between the evaporator temperature of -8 degrees Celsius and condensing temperature of 30 degrees Celsius. The refrigerator R12, okay, so refrigerant which is used over here is R12, is subcooled by 5 degrees Celsius before entering the expansion device, and vapor is superheated to -2 degrees Celsius before leaving to evaporator coil. Draw pH diagram for the process and find COP, power required in kilowatt per ton of refrigeration, and take specific heat of the liquid R12 as 1.235 kilojoule per kg Kelvin and vapor R12 as 0.733 kilojoule per kg Kelvin respectively. Okay students, and the required data or the R12 property table is given over here. Okay, so let us start first. What we will do? First we will try to plot the pressure enthalpy diagram over here. So for plotting the pressure enthalpy diagram, one shall be able and one shall be aware about the saturation dome pattern in the pH diagram, and you also should be aware about the devices that are used, for refrigeration cycle. Okay, so that you should aware about. Right, now here you can see, first of all let us read the data. A food storage requires a refrigeration capacity of 12 TR. Okay, we are drawing the pH diagram, so we will again read the data, and works between the evaporator temperature of -8 degrees Celsius. So let us first plot the pressure on the y-axis and enthalpy on the h-axis. Clear? I hope everyone can see that on the screen. Now let us draw the saturation dome. So saturation dome will look like something like this, as you can see on the screen, by a blue line, blue curvature line. Now what we are given? We are given that the system is working between the evaporator temperature of -8 degrees Celsius. You know that how this arrangement or devices are arranged. Simple: compressor, condenser, then expansion device and evaporator, right? So first of all -8 degrees Celsius. So identify -8 degrees Celsius. So you know that in pH diagram lecture I have told you that if you draw pH diagram and on that diagram if you draw constant temperature line, so that will look something like this. Okay, so everyone, I hope everyone can see -8 degrees Celsius line is drawn over here in the diagram on the screen. That is constant temperature line, right? Okay, now further, and condensing temperature of 30 degrees Celsius. So condensing temperature is 30 degrees Celsius over here students. So let us draw the 30 degrees Celsius line also on the pH diagram. So it will look something like this. And the refrigerant R12 is subcooled by 5 degrees Celsius. Okay, now I have already told you what is the meaning of subcooling. First understand the word subcooling. Meaning of subcooling is very simple. At given pressure, you will decrease the temperature from saturation temperature. Okay, that will be known as subcooling. Subcooling by 5 degrees Celsius is written. That means here, see, the refrigerant is subcooled by 5 degrees Celsius before entering expansion device. Okay, so it is subcooled before entering the expansion device. That means it will be subcooled somewhere over here. That is after condenser outlet. Okay, and you know over here that condenser temperature is how much? 30 degrees Celsius and subcooled by 5 degrees Celsius. So you will have to decrease the temperature by 5. The word by is used. So now the subcooling temperature will be what? 25 degrees Celsius, 30 minus 5, right? So let us plot the line of 25 degrees Celsius. I hope everyone can see that on the screen, right? Now the subcooling line or the subcooling process is highlighted by a black color. Let us draw that how this subcooling can be drawn. So on the pressure enthalpy diagram, as you can see the black line that is highlighting right now on the screen is nothing but the subcooled line. Okay, so that much subcooling is done. And remember, sir, why you have drawn the line horizontal? Because it is advised to keep the condenser pressure as constant. Condenser and evaporator pressure shall be constant throughout its operation. So pressure is constant, but temperature is reduced. Okay, students. Now let us move further. And vapor is superheated to minus 2 degrees Celsius before leaving to evaporator coil. Okay, so that means before leaving to evaporator coil means this is our evaporator. So before leaving this evaporator coil, so if it will leave the evaporator coil, it will enter into compressor. So before entering the compressor, it shall be superheated to minus 2 degrees Celsius. Okay, so now to minus 2 degrees Celsius. Okay, so minus 8 is the evaporator coil temperature. So what we will do? We will do the superheating. So minus 2 degrees Celsius line, let us draw that on the diagram. So I hope everyone can see that minus 2 degrees Celsius line on the diagram. Now what I will do? Here I will draw the superheating process. Okay, so let us draw that. See, a very small line is drawn over here. That is nothing but superheating process before compressor. Okay. So now let us draw the remaining cycle. So the remaining cycle will be drawn by how? Simple. The concept is what? In compressor, reversible adiabatic or isentropic compression shall take place. So let us draw that. You know that how to draw that line. See that line. Okay, so that is nothing but compression line, reversible adiabatic compression or isentropic compression. Then what will happen? Then you know the next procedure is constant pressure heat rejection, that is in condenser. So let us draw that. So as you can see, this whole line is drawn. Okay, now let us move forward. Next process is that you know, expansion device, that is throttling. So in throttling, enthalpy will remain constant, students, right? So here from this point, that is in the subcooled region, we will draw a vertical line because enthalpy will remain constant. So let us draw that. Simple, right? Vertical line. And next, the evaporator. So let us do that also. Okay, so now we have named all the corner points as 1, 2, 3 and 4, right? So 1, 2, 2, that will represent the isentropic compression. 2, 2, 3 will represent the constant pressure heat rejection in condenser. 3 to 4 will represent the isenthalpic process in the expansion device, and 4 to 1 will represent the evaporator or constant pressure heat addition process. Clear, students? Okay, so that is how you can draw the pH diagram from the given data. I hope everyone is clear up to this point. Okay, now what we are supposed to find out? So one task is over. Draw the pH diagram for the process. Okay, now what we are supposed to find out? COP and the power required in kilowatt per ton of refrigeration. Okay, let us do that. So you know that COP is equal to what? Refrigerating effect divided by work done, right? So here refrigerating effect divided by work done. So see, the refrigerating effect that can be written by here, because you know that the endpoints for the refrigerating effect will be corresponding to the evaporator. So you can write the enthalpy difference of H1 and H4, that is H1 minus H4, divided by work done. So work done is equal to, you know that that will represent the endpoints of compressor, that is 2 and 1, so H2 minus H1. right? So that is how this equation on the screen is written, that you very well know. So that means if you can manage to find out H1, H2 and H4, then you can manage to find out the COP. Simple funda. Okay, so let us start the problem. We will find the H1 first. Like for H1, you know that the one point is in superheated vapor region, right? So superheated vapor enthalpy can be given by the equation of H1 is equal to Hg plus Cpv into T superheated minus T saturated. Okay students, so here you can see that H1 is equal to Hg plus Cpv means what? Specific heat at constant pressure for vapor refrigerant. Okay, that is already given. Hg is given to us, that is 184. Sir, how this Hg? See, now it is important. Now, one point corresponding to point number 1, what will be the temperature? Simple, minus 8 degrees Celsius, right? Because 4 to 1 process that will take place during minus 8 degrees Celsius temperature, right? So that is our saturation temperature. So at that saturation temperature, if you find the enthalpy on this saturated vapor line, then that enthalpy will be known as Hg. So Hg is written over here. See, observe the table. In this table 184.07, that is nothing but our Hg, right? Sir, how have you written? I am repeating again. Condenser evaporator is operating at minus 8 degrees Celsius, and that is our saturation temperature, and corresponding to saturation temperature, if you find out the enthalpy of vapor, that will give you Hg. So that is at this particular point, intersection of saturated vapor line and 4-1 line. Okay, so that is equivalent to 184.07. So Hg is already given. Cpv, so observe the given data students. So for vapor, specific heat is already given, that is 0.733 kilojoule per kg Kelvin, right? Next, T superheated. So here T superheated. So that means nothing but the temperature of point number 1. Okay, so here point number 1 temperature will be minus 2 degrees Celsius, that you know, because it is already given in the data that you have to superheat from minus 8 degrees Celsius to minus 2 degrees Celsius. So corresponding to minus 2 degrees Celsius, if you convert it in Kelvin, that will represent 271 Kelvin. And saturation temperature is how much? Simple, minus 8 degrees Celsius. So minus 8 degrees Celsius, corresponding to that, convert it into Kelvin. So that will be equivalent to 265 Kelvin. Very much simple. So you have all the values, substitute in the equation, you will have the value of H1 as 188.468 kilojoule per kg Kelvin. I have also highlighted the value over here also. Okay, now next task is to find out H2. So let us do that. So for finding out H2, the 2 point is also in superheated vapor region, right? So you know that the equation of superheated vapor is H2 is equal to Hg plus Cpv T superheated minus T saturated, that you know. Now here Hg. So now you just think about how the value of Hg can be found out from the table. See, corresponding to 2 to 3 process, what is the saturation temperature? Saturation temperature is 30 degrees Celsius. So for 30 degrees Celsius, what is the value of enthalpy of vapor? So enthalpy of vapor value is 199.62. So that is nothing but the enthalpy at this particular point, see, this point. So that will give us Hg. Okay, enthalpy of dry vapor. Okay, so that is Hg. So Hg is already given, that is 199.62 kilojoule per kg. Cpv is already given in the data, that is 0.733 kilojoule per kg Kelvin. T superheated and T saturated. So here T saturated we know that is 30 degrees Celsius, right? So corresponding to that 303 Kelvin will be there. Okay, but superheated temperature, that is point number 2, that is not given to us students. Okay, so T superheated is not known to us. So now the task is what? Now the task is, if you want to find out H2, then you shall manage to find out T superheated. And this T superheated shall be found out first. So in order to find out this T superheated, what is the idea? The idea is, observe that 1 to 2 process. See, 1 to 2 process is reversible adiabatic process or isentropic compression process. Now meaning of isentropic means what? Entropy will remain constant. So as you can see, here what we will do, first we will find out the value of S2. Okay, so now value of entropy at point 2, that is superheated vapor. So for superheated vapor, how equation can be written? You know, you have already studied the vapor cycle, right? So that you know. So S2 is equal to Sg plus Cpv ln T sub by T set. So in this equation, Sg is what? At point number 2, we should have the Sg. So 2 to 3 process. Sg is what? Corresponding to 2 to 3 process, the value of entropy at this particular point. So that is already given, because you know that corresponding to 2 to 3, the temperature is 30 degrees Celsius, right? So if the temperature is 30 degrees Celsius, then at 30 degrees Celsius, entropy of vapor is already given, that is 0.6853, right? So Sg we can manage, Cpv we can manage, but our T saturation we can manage, but T superheated, that is what we are supposed to find out. But here S2 we don't have. So that means if you want to find out T superheated, then you have to find out S2, right? So now S2 and S1 are same, I told you, right? So S2 is equal to S1. Now S1 is what? So S1 is also superheated vapor. So for superheated vapor, what you can write? S1 is equal to Sg plus Cpv ln T sub by T set. Okay. So now what will happen? Very simple, students. Here you can see Sg. So Sg is equal to what? So see, this one point is associated to 4 to 1 process, and corresponding to 4 to 1 process, minus 8 degrees Celsius is the saturation temperature. So for minus 8 degrees Celsius temperature, what will be the entropy of the vapor? 0.7007. So that is nothing but the entropy of dry vapor at this particular point. So Sg is equal to 0.7007 kilojoule per kg Kelvin. Plus Cpv. Cpv is already known to us, that is 0.733 kilojoule per kg Kelvin. Then T sub by T set. Okay. So here T sub by T set. So here T superheated is given? Yes, because point number 1, corresponding to point number 1, the temperature is how much, student? Minus 2 degrees Celsius. So that is our T superheated. So that is 271 Kelvin. And T saturated is what? T saturated is minus 8 degrees Celsius. So convert it into Kelvin. So 265 Kelvin. So now in this equation of S1, we have Sg, Cpv, T sub, T set. So you can find out the S1 simple as 0.717 kilojoule per kg Kelvin. So this S1 is equivalent to our S2, because S1 and S2 will be same, because the 1 to 2 process is isentropic process. Simple, students, right? So here our S2 will be also equal to 0.717 kilojoule per kg Kelvin. Clear? Now we have the S2, right? So what we will do? Sg is also known to us. Sir, how have you found out Sg? Simple. See, 2 to 3 process, because see, whenever I am talking about entropy of second point, then I will have to consider 2 to 3 process, and whenever I am talking about the entropy or any property of one number point, then I will have to consider 4 to 1 process. Now what will happen here? See, Sg is equal to what? 0.6853 kilojoule per kg Kelvin. How? Let us understand. So corresponding to 2 to 3, the saturation temperature is 30 degrees Celsius, and corresponding to 30 degrees Celsius, the entropy of the vapor is 0.6853 kilojoule per kg Kelvin. That is why this one is written like this. Cpv is already known to us, students, that is 0.733 kilojoule per kg Kelvin. T superheated and T saturated. So T superheated is our funda or aim to find out, right? And T saturated, so T saturated is 30 degrees Celsius, that you know, right? So T saturated is 303 Kelvin. So in this equation of S2, we have S2 also, we have Sg also, we have Cpv also, right? So we can find out T superheated. Okay, so here what we will do, we will reduce the equation and solve one by one step. Now here see, 0.0432 is equal to ln T sub by T set. So here this can be also written as e raised to power of 0.0432 is equal to T superheated by T saturated. So you can make T superheated as the subject. So you will have the final answer of the T superheated as 316.37 Kelvin. Okay, because T saturated is already given, students, that is 303 Kelvin. Okay, so T superheated is found. Okay, now we will use this T superheated in the equation of H2, right? So we can find out the H2 as 199.62 plus 0.733 into 316.37 minus 303, right? So H2 is equal to 209.42 kilojoule per kg. Okay. Now H2 is done. Now what we are left with? We are left with H4. See, whether you can find H4 or you can find H3, both will be same because that is isenthalpic process, right? So H3 and H4 both will be same. Okay, so here what I will do, 4 point is in vapor region, wet vapor region, and third point is in pure liquid region. So I will find out the H3. Okay, so let us find out the H3 because my H3 and H4 will be same. Okay, so now H3. So how this H3 equation can be written? Let us write. Let us understand that. So H3. See, on the pH diagram corresponding to point number 3, if you draw the vertical straight line, so it will have some enthalpy. Let us say for example 100. Just for example. And corresponding to 3 dash point, if you will draw a straight vertical line, then corresponding to that the enthalpy will be greater than 100. That is, let us say for example 150. Right? So that means if you want to find out the enthalpy at point number 3, then you will have to neglect certain value from the enthalpy of point number 3 dash. Okay, so what do you mean? I mean H3 is equal to H3 dash minus CPL T3 dash minus T3. Okay, 3 dash is corresponding to saturated liquid point and 3 is corresponding to pure liquid point. Okay, so that is how you can find out the enthalpy at point number 3. That is, you have to subtract certain value. See, Cp delta T at constant pressure, Cp delta T for liquid, that will give you the enthalpy. Okay, so that is how this equation is written. Okay, so H3 dash minus CPL, not V, because here liquid state is there. See, this whole is in liquid state. So that is a CPL into T3 dash minus T3. So you will take here higher temperature minus lower temperature. That is obviously T3 dash will be higher, T3 will be lower. Okay. So now T3 dash minus T3 is how much? You know that, right? Because the liquid is subcooled or refrigerant is subcooled by 5 degrees Celsius, or you can say 5 Kelvin. So T3 dash minus T3 is directly 5 Kelvin. Now H3 dash. So H3 dash is how you can find out. See, simple. 3 dash is nothing but your saturated liquid point, and corresponding to that saturated liquid point, what is the saturation temperature? 30 degrees Celsius. So in 30 degrees Celsius, what is the value of enthalpy for liquid? 64.559, right? So 64.59 will be the value of H3 dash. That is nothing but HF at 30 degrees Celsius, right? Now let us move forward. CPL is already given in the given data. See students, 1.235 kilojoule per kg Kelvin. Okay, so CPL is given. T3 dash minus T3 is already given. I told you 5 Kelvin, right? 5 Kelvin or 5 Celsius, both will be same. Okay, because the Kelvin and Celsius relation is in proportion. Okay, so 5 Kelvin. Now linear proportion. Okay, so now let us find out the value of H3. So substitute all this value. So you will have the value of H3 as 58.415 kilojoule per kg. Okay. Now we have all the values H3, H4, H1, H2. So let us find out the COP. So substitute all the values. So you will have the value of COP as 6.2. Okay students. Now understand over here students. See, the refrigeration effect is already given to us, that is 12 ton. And 12 ton of refrigeration is equivalent to how much? 42 kilowatt. So refrigerating effect is ultimately given to us, that is 42 kilowatt. And you know from the fundamental concept of the cycle that refrigerating effect can also be written as mass flow rate into H1 minus H4. So how mass flow rate is written? Why mass flow rate is written? Simple. See, if you can also write the refrigerating effect as H1 minus H4. But if you write it in H1 minus H4, then unit will be kilojoule per kg. And if you write down in form of m dot H1 minus H4, then the unit will be kilowatt, because you are multiplying with the mass flow rate. And I have already explained this to you, that how the effect of multiplying the mass flow rate will give you the result for conversion of kilojoule to kilowatt. Clear? So that is the refrigerating effect. So this refrigerating effect and this is also refrigerating effect, you can compare both these two. So if you will do so, you can find out value of m dot. So value of m dot will be equal to 42 divided by h1 minus h4. We have the value of h1 and h4 here, right? So substitute that over here. So you can find out the m dot as 0.3229 kg per second. Clear, students? That is nothing but the flow rate of the refrigerant throughout this cycle. So in per second, from a single point in the pipeline of the refrigerant cycle, the flow will be 0.3229 kg. Okay, per second from any cross section. Okay, I hope everyone is clear up to this point. Now, that means what? That means what we are supposed to find out? We are supposed to find out power required in kilowatt. Okay, so power required in kilowatt, let us find out. Now power required is equal to what? M dot H2 minus H1. Simple, right? So we can write down H2 minus H1 and we can find out the power. Okay, so if we will do so, let us substitute the value over here and the final value of the power will be this. Okay, so that is how you can find out the power also. So today we are going to keep up to this point. Thank you.